You know, people often come to me, students, reporters, just people at parties, and they hold up two magnets, just two ordinary bar magnets, and they push them together. You know the feeling. You push the two north poles together or the two south poles, and you feel that thing, that resistance, that cushion of air that isn't air. It's spongy. It pushes back. And they look at me with this look of wonder, which I love, by the way, never lose that, and they ask, Professor Feynman, what is happening between these two bits of metal? Explain it to me. Why do they repel each other? And they expect a simple answer. They expect me to say, oh, well, it's like a rubber band, or it's like water pressure. They want an answer in terms of things they already understand. But I can't do that. I cannot explain how magnets work in the way you want me to. And the reason I can't explain it is not because I don't understand the physics. We understand the physics very well. The equations are beautiful. The reason I can't explain it is because of you. And it's because of the English language. And it's because of the nature of why. So we are going to spend some time on this. I don't want to give you a cheat answer. I want to give you the truth, and the truth requires us to back up, way back. You see, when you ask why in physics, it's a very dangerous question. Let's take something simple. Suppose you ask me, why did Aunt Minnie slip on the ice? Well, that seems like an easy question. I can tell you, she slipped because the ice was slippery. Then you say, okay, I understand. If you're satisfied, you walk away. But wait a minute, why are you satisfied? All I did was change the word slip to slippery. I haven't told you anything deep yet. If you are a curious person, and I hope you are, you might ask, but Professor, why is the ice slippery? Now we are getting into trouble. Now I have to say, well, ice is slippery because when you stand on it, the pressure of your weight momentarily melts the surface, creating a tiny layer of water, and water is slippery. Actually, it turns out that's not entirely true, but it's the old story. But let's say that is true. Then you ask, why does water make it slippery? Now I have to talk about friction. I have to talk about molecules. I have to say, well, the water molecules are liquid. They can roll over each other, whereas the ice is solid. And you ask, why do molecules roll over each other? And suddenly we aren't talking about Aunt Minnie anymore. We are talking about atomic forces. We are talking about quantum mechanics. We are talking about how atoms stick together or don't stick together. You see the problem? Every time you ask why, you go down a layer. You go deeper into the onion. And eventually, you hit a layer where I can't tell you it's like a rubber band anymore, because the rubber band itself is made of atoms. If I explain the magnet in terms of rubber bands, I haven't explained anything, because the rubber band is an electromagnetic phenomenon too. So if you want to understand the magnet, you have to be willing to be honest about what you know and what you don't know. You have to allow me to take you to a place where things are strange, a place where common sense doesn't work very well. Let's look at this sensation again, the pushing. When you push the magnets, you feel a force. We use that word a lot. You feel it in your muscles. You think, okay, force is something I do. I push the chair, I lift the glass. You have a feeling for force. It's mechanical, it's contact. This is the prejudice of the human animal. We are big, clumsy things. We live in a world of medium-sized objects, rocks, trees, water, other people. When we want to move something, we have to touch it. We have to grab it and shove it. So our intuition, our gut feeling, tells us that force requires touching. So when you hold the magnets and they are not touching, but they are pushing, you get spooky. You think, this is action at a distance. This is magic. But let me ask you a question, a very serious question. When you sit on your chair, are you touching the chair? I want you to really think about it. You feel the chair on your bottom. You feel the pressure. But if we looked at the interface between your pants and the chair with a microscope, super microscope, what would we see? We would see fibers of cotton or wool. And if we looked closer, we would see molecules. And if we looked closer, we would see atoms. Now, do the atoms of your bottom actually touch the atoms of the chair? No, they do not. If the nucleus of an atom was a marble sitting in the middle of a football stadium, the electrons would be tiny gnats buzzing around the top of the bleachers. The atom is mostly empty space, mostly nothing. So when you sit on the chair, what is actually happening? The electrons buzzing around the atoms of your body are repelling the electrons buzzing around the atoms of the chair. They are pushing against each other. They get close, very close, but they never touch. There is a field, an electrical field. The force that holds you up, the force that stops you from falling through the chair and down to the center of the earth, is the same force as the magnet. It is the electromagnetic force. So you see, you are shocked by the magnet because it works across an inch of air. But you are not shocked by the chair because the distance is a billionth of a centimeter. But it is the same thing. It is exactly the same thing. The only difference is the distance. Because the magnets are arranged in a special way, the force extends out further, so your clumsy human hands can feel it. But the contact force you feel when you punch a wall, that is electrical repulsion. So when you ask, how does the magnet work? And you want me to explain it in terms of touching or rubber bands, you are asking me to explain the fundamental force in terms of the complex derivative force. You are asking me to explain the foundation of the building in terms of the wallpaper. I can't do it. I have to explain the wallpaper in terms of the foundation. So are you ready to accept that? Are you ready to accept that touching is an illusion? That nothing really touches anything? If you can accept that, then we can talk about magnetism. Now, to understand the magnet, we have to look at matter. We have to look at what stuff is made of. Everything is made of atoms. You know this, but you probably think of atoms as little solar systems. A nucleus in the middle and electrons orbiting like planets. That's the picture they draw in school books. It's a terrible picture. It's wrong. Well, it's not totally wrong, but it's wrong enough to confuse you. Electrons aren't little planets. They are clouds. They are waves. They are probability distributions. But for the sake of our magnet, let's simplify just a little bit. Let's imagine the electron does have a property called spin. Now, don't imagine a top spinning. I mean, you can imagine a top, but don't take it too literally. Just know that the electron has an orientation. It has a little arrow attached to it. It's acting like a tiny magnet itself. Every electron in the universe is a little magnet. So you are made of magnets. The chair is made of magnets. The air is made of magnets. So why aren't you sticking to the refrigerator? Why doesn't the book fly off the table and stick to the ceiling? If everything is made of magnets, why isn't the whole world just one big clump of stuff stuck together? This is where it gets interesting. And most stuff, like a piece of wood or plastic or your skin, the electrons are jiggling around. They are buzzing. And their little magnetic arrows are pointing everywhere. One points up, one points down, one points left, one points right. They cancel each other out. It's chaos. It's a wash. On average, there is no magnetism. The net result is zero. It's like a crowd of people all shouting different things at the same time. You just hear noise, but quiet. Iron is special. Nickel and cobalt too. But let's stick with iron. In iron, due to some very complex quantum mechanical reasons, which we can get into later if you want a headache, the electrons like to line up. They are like a crowd of people who suddenly decide to all chant the same word. They all turn their heads to the right. But usually in a normal piece of iron, like a nail, this lining up only happens in small patches. We call them domains. So you have a microscopic neighborhood where everyone is looking right, but the neighborhood next door, they're all looking left, and the next one is looking up. So even in iron, usually they cancel out. The nail isn't a magnet yet. But if you put that iron in a strong magnetic field, if you force it, or if you heat it up and cool it down in a magnetic field, you can convince all those domains, all those neighborhoods to agree. You get them all to face the same way. Billions and billions of trillions of electrons, all spinning in sync, all their little arrows pointing north. Now you have a magnet. Now the silence of the crowd becomes a roar. The force is no longer microscopic. It adds up. It extends out of the metal. It reaches into the space around it. And this is where we have to talk about the field. I know. The field. It sounds like science fiction. What is the field? Is it a fluid? Is it a gas? No. The field is a mathematical description of what would happen if you put something there. This is very abstract, I know, but try to visualize it. Imagine the air around the magnet is filled with a tension, like the air is stressed. When you bring another magnet into that space, it feels that stress. If you bring the north pole of one magnet to the north pole of the other, You're trying to shove these aligned electrons against the grain. The space between them contains energy. The field lines, these invisible lines of force we draw, they want to spread out. They don't want to be compressed. So when you push them together, you are actually pumping energy into the space between the magnets. You are compressing the field. And nature hates that. Nature wants to lower its energy. So it pushes back. It says, get away. I need room. That push, that is the release of energy. That is the field trying to relax. But wait, I still haven't answered the deep question, have I? I told you what happens. I told you about electrons lining up. I told you about the field. But why? Why do electrons repel each other? Why does a moving charge create a magnetic field? Now we have to go to the deepest level. We have to go to Einstein. And this is the part that blows my mind every single time I think about it. Magnetism isn't real. Okay, that's not quite right. It is real. You feel it. But magnetism is actually just electricity, seen from a different perspective. Magnetism is a consequence of relativity. Let me explain. You know Einstein's special relativity? It says that length contracts and time slows down when things move very fast. You think, oh, that only matters for spaceships going at the speed of light. Wrong. It matters for the wire in your wall. Imagine a copper wire. You have protons, positive, standing still in the wire, and electrons, negative, flowing through it. That's current. Now imagine a cat is walking next to the wire. Just a normal, neutral cat. Nothing happened. But now imagine the cat is charged. It has static electricity on its fur. And let's say the cat is moving along with the electron. From the cat's perspective, the electrons in the wire are standing still because the cat is moving at the same speed. But the protons are moving backwards relative to the cat. Because of relativity, the space between the moving protons shrinks. They get squished together. The density of positive charge goes up. So to the cat, the wire suddenly looks positively charged. It gets pushed away. We call that push magnetism. But it's really just the electric force distorted by the fact that things are moving. When you hold those two magnets in your hand, you are feeling the effects of relativity. You are feeling the universe contracting and expanding at a microscopic level because of the motion of electrons. So you are holding Einstein in your hand. That tiny invisible motion of electrons inside the metal is magnified by the billionth, so strong that you, a giant creature, can feel it with your finger. Isn't that spectacular? So when you ask, how does it work? I can't tell you it's like a rubber band, because it's not. It is the interplay of space and time and electrical charge. It is the fundamental machinery of the universe showing itself to you. You see, the reason we struggle with this, the reason you might still be frowning and thinking he still hasn't explained what the force is because we are trapped in our evolutionary history. We are apes. We are very smart apes, but we are apes. We evolved to understand throwing rocks, climbing trees, and peeling bananas. We evolved to understand the mechanics of things we can see. If I throw a rock, I know why it moves. I pushed it. If I pull a rope, I know why the log moves. I pulled it. We have a mechanical view of the world. Gear A turns gear B. But the universe at its bottom is not mechanical. It is not made of gears. It is not made of ropes. It is made of fields. And a field is something we have no evolutionary reason to understand. We can't see it. We can't smell it. We can't eat it. So when we encounter it, like in a magnet, we try to force it into a mechanical analogy. We say, are there little particles flying back and forth? Well, actually, in quantum field theory, we do say there are virtual photons. But let's not get into that. It confuses the picture for now. And we want a picture. But nature doesn't care about our need for a picture. Nature is there doing her thing, whether we can visualize it or not. The math works. The equations of Maxwell, the equations of quantum mechanics, they predict exactly how much that magnet will push. They predict it to the 10th decimal place. But the mental images, that is up to you. And this leads me to a very important point about science. Science is not about why. I know that sounds terrible. Science is not about why, but it's true. Science is about how. Why implies purpose. Why implies that there is a reason behind the curtain. Why does the Earth go around the sun? Because of gravity. Why gravity? Because space is curved. Why is space curved? Because mass tells it to. Why? Eventually, you hit the bottom, you hit the bedrock. You hit a statement that simply is mass attracts mass. Electrons repel electrons. If you ask me, why do electrons repel electrons? I have to look you in the eye and say, because they do. That is the rule of the game. This universe has a rule book. We didn't write it, we just found it. And rule number one is, like charges repel, there is no underneath that rule. That is the bottom. So the magnet is actually a window into the axioms of existence. When you feel that push, you're touching the raw code of the cosmos. You aren't touching a mechanism, you are touching a law. And I think that is much more beautiful than a rubber band. Don't you? I want you to try something for me. Get 2 magnets. If you don't have them, go buy them. Toy store, like hardware store. Sit at your table, clear away the papers, put the magnets down, close your eyes, push them together. Feel that springiness, feel that life. It feels like there is something there, right? It feels like there is a substance between them. But open your eyes. There is nothing. That is the ghost in the machine. That is the electromagnetic field. It is filling the room right now. It is holding the atoms of your body together. It is carrying the light from the lamp to your eye. It is carrying the signal from the radio station to your car. It is everywhere. It is the water we swim in. But we are too fish-like to notice it, except with the magnets. The magnets are the only time the fish sees the water. When I look at the magnet, I get a shiver. Not because I know the equations. The equations are just tools. I get a shiver because I realize how much is happening in the empty space. It's alive. The space is alive with potential. And the fact that we, little biological machines made of carbon and water, can figure this out, that we can scratch some symbols on a chalkboard and describe this invisible dance, that is the miracle. So you asked me to explain how magnets work. And I told you I can't. Not in terms of the things you know. I can't explain it in terms of common sense. I can only explain it in terms of the strange, beautiful, jiggling, relativistic reality of the universe. And if you go home tonight and you're lying in bed and you think, I still don't quite get it. It still feels like magic. Good, because it is magic. It's just magic that follows rules. And our job as scientists, as thinkers, as human beings, is to find those rules and to admire the show. You know, we take these things for granted. You go to the refrigerator, you stick a picture of your dog on it with a magnet, and you walk away to get a sandwich. You don't even think about it. But imagine you are a Greek shepherd thousands of years ago. You are walking on Mount Ida. You have shoes made of wood, held together with iron nails. And suddenly you step on a black rock, and your shoe sticks to the rock. You pull your foot up, and it pulls back. You think, oh, what is this? Is there a spirit inside the rock? Is it alive? And they called it lodestone, magnetite. It was the only thing in the world besides the earth pulling you down that exerted a force without touching. Gravity pulls you down. But this rock, it could pull you sideways. It could pull you up. It defied the natural order of things. For 2,000 years, nobody knew why. They thought the rock had a soul. They thought it fed on iron. They thought it free, and if you rub garlic on it, it would stop working. It doesn't, by the way. Please don't put garlic on your magnets. It just makes them smell. But the real breakthrough, the moment the universe cracked open, didn't happen with the rock. It happened with a wire. We have to talk about Hans Christian Ørsted. It's 1820. He's a Danish physicist. He's giving a lecture. It was a simple lecture. He has a battery, and he has a wire, and he has a compass. Now, everyone knew about electricity, lightning, sparks, batteries, and everyone knew about magnetism, compasses pointing north, but everyone thought they were two different things, like cats and dogs, totally different animals. So Ørsted is lecturing, and he turns on the current in the wire, and purely by accident, or so the story goes, the compass needle, which was sitting nearby, moved. It didn't point to the wire. It didn't point away from the wire. It pointed around the wire. It pointed in a circle. This is crazy. Forces usually push or pull. Gravity pulls straight in. And if I push you, I push straight back. But this force, it was acting sideways. It was a rotational force. Oersted realized something that changed the world. Electricity in motion creates magnetism. There is no magnet substance, and there is no magnet fluid. There is only moving electricity. So when you look at that black rock or that bar magnet in your hand, you have to ask, where is the electricity? I don't see any batteries. I don't see any wires plugged into the wall. And this brings us back to the atom. Inside that rock, there are billions of tiny currents, and the electrons spinning around the nucleus are little loops of current. They are little wires. So a permanent magnet is actually a collection of billions of microscopic electromagnets, all running without a battery, all running forever. And that brings up a question that I know you're dying to ask. You're thinking, wait a minute, Professor, you said the electron is spinning forever. You said it's a little current running forever. Doesn't that violate the laws of physics? Doesn't it run out of energy? If I have a top spinning on the table, eventually it falls over. Or friction stops it, air resistance stops it. So why doesn't the electron stop spinning? Why doesn't the magnet run out of magnetism? If I stick a magnet to the fridge, it stays there for 10 years. It's fighting gravity. It's holding the paper up. Is it doing work? Is it burning fuel? No. This is a very common mistake. Holding something up is not work. If I hold a heavy book in my hand, my arm gets tired. I feel like I am doing work. But that is just because my muscles are inefficient biological machines. They are twitching. They are burning sugar to stay tight. Boom! But suppose I put the book on a table. Does the table get tired? Does the table have to eat a sandwich to keep holding the book? No. The table just sits there. The atoms of the table push up against the book with that same electrostatic force we talked about earlier. It costs zero energy to just be there. The magnet on the fridge is the same. It is magnetically locked to the steel door. It is sitting in a potential energy well. It doesn't cost any energy to stay there, just like it doesn't cost a rock any energy to sit at the bottom of a valley. But what about the spinning electron? Why doesn't it slow down? Because what would it rub against? Think about it. Friction is when big things bump into other big things and transfer energy. But an electron is a fundamental particle. It is the bottom. There is no air inside an atom for it to rub against. There is no surface for it to scrape. It is in a state of quantized angular momentum. That's a fancy way of saying it spins because it is a spin. If it stopped spinning, it wouldn't be an electron anymore. So the magnet is a window into a world where friction doesn't exist. A world of perpetual motion, not the fake perpetual motion scammers try to sell you, but the real eternal motion of the quantum world. So we have electricity and we have magnetism. And Oersted showed us that moving electricity makes magnetism. But then came a Scotsman, James Clerk Maxwell. Maxwell was a genius, a real genius. He looked at this and said, if moving electricity makes magnetism, does moving magnetism make electricity? It's a symmetry argument. Nature loves symmetry. If A causes B, does B cause A? And it turns out, yes. If you take a magnet and you shove it into a loop of wire, you get a spark, you get electricity. But only while the magnet is moving. If you hold the magnet still inside the wire, nothing happens. So, a changing electric field creates a magnetic field. This changing magnetic field creates an electric field. Maxwell wrote this down in 4 equations. They're short, but you can print them on a t-shirt. I have one, actually. But when he solved these equations, he found something terrifying. If I wiggle an electron here, it creates a changing electric field. That changing electric field creates a magnetic field. That changing magnetic field creates another electric field, and that one creates another magnetic field. They leapfrog. They jump over each other. The energy travels out from the electron, propagating through space. Maxwell calculated the speed of this wave. He took the numbers from electricity experiments and the numbers from magnetism experiments, totally separate numbers, and he plugged them into his equation. And out popped the number, 300,000 kilometers per second. Maxwell must have fallen off his chair because he knew that number. That was the speed of light. Until that moment, nobody knew what light was. They thought it was a separate thing, but Maxwell realized light is a wave of magnetism and electricity wiggling together. The magnet in your hand, the force field around it, it is made of the same stuff as the light entering your eyes right now. The only difference is that the magnet field is static, mostly, and light is a field that is vibrating back and forth 1 trillion times a second. So when you ask, how does a magnet work, you're also asking, what is light? It is all one thing. It is the electromagnetic field. We live inside it. We are made of it. Chemistry is just the study of how these electromagnetic fields interact. Biology is just the study of complex chemistry. So in a way, you're just a very complicated pattern of electromagnetic fields walking around asking questions about itself. But wait, I still have an answer to a specific question. If everything has electrons and all electrons are magnets, why is wood not magnetic? Why is water not magnetic? Why only iron, nickel, cobalt, and a few rare earth metals? Why is the club so exclusive? This requires us to look at how electrons live inside the atom. Electrons live in shells, like layers of an onion, and inside those shells they live in pairs. This is the Pauli exclusion principle. It's a rule that says you two electrons can live in this room, but one of you has to spin up and the other has to spin down. They are like an old married couple. One looks left, the other looks right. They cancel each other out. In almost every element in the periodic table, carbon, oxygen, gold, copper, the electrons are mostly paired up. For every north electron, there is a south electron right next to it. Net result, zero magnetism. But iron is the rebel. In the iron atom, there is a specific shell, the 3-day shell, if you want to be technical, that has a problem. It has room for 10 electrons, but iron only has 6 electrons to put in there. So how do they arrange themselves? Do they pair up 3 and 3? No, electrons repel each other. They want space. So the first 5 electrons say, I'm taking my own room. They all sit in separate funks and they all face the same way. They all spin up. So you have 4 or 5 electrons in every single iron atom that are unpaired. They are screaming north and there is nobody to cancel them out. That is a huge amount of magnetism for one tiny atom. But that's only step 1. Now you have a magnetic atom. But a nail is made of trillions of atoms. Why don't the atoms just cancel each other out randomly? In most materials, they do. But in iron, the atoms are communicative. They talk to their neighbors. It's called the exchange interaction. It's a quantum mechanical effect. Again, spooky stuff. Where the electrons say, hey neighbor, if I spin this way and you spin this way, we can lower our energy state. They find it comfortable to align. It's like peer pressure. If one atom points north, the neighbor feels better. If he points